This is the ice skater problem from lecture 21, October 31st. It says that we have a young lady on ice skates who is doing a twirl. So with her arms out or stretched. And so she has an initial angular momentum Li. She pulls her arm in and she's spinning in the same direction, but she now has a final angular momentum L final. So the question is, what happens to her physically as she brings her arms in? So just like linear momentum, angular momentum is also conserved. So we can say that the initial angular momentum is equal to the final angular momentum. Angular momentum by definition is moment of inertia times the angular velocity. So we make some substitutions and we get the initial moment of inertia times omega I is equal to, again, the final moment of inertia times omega F. If we solve for omega F, we know that she now has moment of inertia initial, omega initial divided by moment of inertia final. Now why is this important and why does this matter? Well, as she brings her arms in, she redistributes her mass. By redistributing her mass, she changes her moment of inertia I. This moment of inertia is important. We know that with her arms outstretched, her moment of inertia initially is greater than her final moment of inertia. And that means if we go back up here to our relationship, omega F is equal to moment of inertia I, omega I over moment of inertia F, we know that the initial over the final is going to be greater than 1, so we know that her angular speed must increase. So this is what happens when she brings in her arms. The second part of this problem says, what's happening to her kinetic energy? Well, if we start off with the idea that the kinetic energy for rotational is going to be 1/2 moment of inertia I, omega I, then we know that she should also have some sort of final kinetic energy that's equal to 1/2 the moment of inertia F, omega F. Okay, so now on her final kinetic energy, we can make a substitution of omega F that we solved over here earlier. So here it is. We're going to substitute it into here. So we get a final kinetic energy that says it's 1/2 IF. Okay, and now we have to square all this. So we have moment of inertia initial, omega initial, moment of inertia final, all of this quantity squared. So we know that we could actually do a substitution. We get rid of this. This has a 2, it now has a 1. This is now quantity squared at the top. So we have kinetic final is equal to 1/2 moment of inertia I squared, omega initial squared, all over moment of inertia final. So what exactly does this mean? Well, if we make a little bit more substitution, so the kinetic final energy, if we rearrange a little more, it can take on a shape of moment of inertia initial over moment of inertia final times 1/2 moment of inertia initial omega I squared. If we take a look at that, this quantity is now the initial kinetic energy. Now earlier we said that her moment of inertia was greater initially and less finally. So now I have a large number divided by a small number, which is bigger than 1, which says that her kinetic energy had to increase.